I can't help myself. I just started on problem 8. So now we'll just answer it off the bat. We're looking for a point with vertical tangent. There seems to be one and only one. The cubic root of a times 0.0. Then we have order 2. No, then we have order 3. And the same reason as before, I'm looking for the point, point of inflection. So there should be 2. So 1. Here should be 2. And order order 4. That's a point that ends here, so we need to find a point, and we learned that from the last exercise. There is one up here. So this one squared gives this one, because rubbish. This one squared goes down here, and then the negative, etc. So there should be 2. And I would like to be more explicit and do the mathematics in Mabel as well, so I get a drawing of it. And to do that, we need to find the x value of 2p, like we did in exercise 1. So, now this is d in formula, I guess it's 7.2, which we have been using repeatedly. Now the derivative squared, that's 3x to the second. So that's 9x to the fourth divided by 4. Y squared, that's x to the third minus a. So we put them on a common denominator. This gives minus 8x to the fourth plus 2xa plus 9x to the fourth, x to the fourth plus 2xa we can put x outside the parenthesis. Doesn't really help us, does it? point of inflection we can of course find by saying that this should equal x. The point of order 2 we have found, so let's try to find the point of inflection doing that. Divided by this gives x, so we do like that. I just wondered if it was, oh yeah, it's 4 down here. So it's the cubic root of 2 times this number. So it's, I don't know, 1.3 up here. Drawing is not quite exact, but who cares? So that's the point of inflection. And then the point up here should we really try to find it, or should we just call it a day? I think we should try to find it. So that's where this gives x, a, the cubic root of a, I can only move the whole thing. So let's do it down here. Doesn't come out very nice, so I'll just believe in the geometry that up to the inflection point it curves to the right, so it will intersect the x-axis to the left of the cubic root of a, and after the inflection point it curves to the that doesn't mean that the intersection point will increase monotonically, does it? No. It seems credible that it does, but it's actually, we need actually to solve this equation to show that it is true. I'll just work a little on it. I have no idea what to do with this. If A equals unity, let's assume there's some scaling. So if x is 1, it gives -9. (4x to the third minus 2x and was +4 -4. So it takes quite a while before it becomes positive. Then it does at 4 point something. So I haven't given a formal proof that we only have 2 points of exact order 4. I don't know really how to do that easily. Of course, we can solve this guy. And there will be a negative solution as well, of course. There we have it. And so the value at 0 equals -4. There we have it. So there's a positive root and a negative root. And then I wonder, root of this and root of that. All right, we don't want that. Numeric. All right. We still don't want that. So let's say 4 point. Now, why is that? .2 2 point. Why does it do that? Oh, it's not one number, it's 4 numbers. I don't want to read that. When you do this, it stands to reason that there only are 2 real roots. So let's just leave it at that. So I don't know really how to show that there are only 2 points of order 4 in an easy way. I want to have an elegant proof of it, not something that is heavy. So and I don't know how to do that at the moment. So bye. It's pouring down. I couldn't let go of problem 8. Now, there really is a symmetry, so the solution will be proportional to the cubic root of A. So this is the one we have to investigate. And I seem to remember that there was some procedure for determining the number of roots. And so I Googled it. And first we have Descartes' rule of signs. So you can find it on I'll just show you the method. We take the numbers, we order the coefficients in decreasing order, and then count the number of signs of the coefficients. There's 1 from plus to minus 4. There's 1 change of sign. And then there'll be at most 1 positive root. And of course it's easy to see there is 1, because at naught it gives minus 4 and it will tend towards infinity. So that proves that there is exactly 1 positive root, as I claimed. If we do the same for the negative coefficients, then we must change these 2 signs. So that means we have, it's plus, plus, minus, then there's 1 change of sign. So that gives at most 1 negative root. And well, that might be, that will be, there is a negative root. That was using Descartes' principle, Descartes' rule of signs. More well known is Durham's method. It's actually a theorem. So first we differentiate it, and then we compute the consecutive reminders by division. So let's try to do that. Mathematics have a lot of technique, and one cannot know them all. So So minus the, we'll just do it. So of course it's a third x a third times this, that's minus 4. That's weird. Oh, that differentiated gives that, so it's okay. And then 2/3 x. 2 minus 2/3 give minus give 4/3 x minus 4. So that's, I don't know how to enumerate them. We say P2. And then we take the remainder there. That's a little more complicated. So the first one gives 9/4 x squared. Nine-fourths, that's 3, that's minus 27 x squared. And then 9/2. Now what am I doing? I have to multiply this by the thing in the second parenthesis. So this must be multiplied by this, so it gives 9x squared plus 9x squared subtracting gives minus 21. It's much better doing it on Maple, of course. I don't recall the command I would need to use, so maybe if I could do it correctly, it would be quite well to do it by hand. So let's try that. So divided by, oh my God. No. So this was a very poor example for that technique, I should say. On the other hand, it's just multiplying by a constant shouldn't really do anything, should it? So I believe instead we could just use, or that doesn't really change stuff, doesn't make it better here, really. So minus 21 divided by 4/3, that's minus 63/4 x. So that gives minus 21 x squared minus 63 x. 63x minus 2. And 63x divided by 4/3 plus 186/4. So they cancel each other. That gives 389. And then times 4. It's like a plus. So it gives minus minus 2 minus 199. And we have to change sign. It's 191. So, Sturm's theorem was, I think we should, I just have to read it. The number of sign variations at zeta of the Sturm sequence. All right. So to find the all the real roots, we'd let x go to minus infinity, plus, minus, minus, plus. At infinity, it's plus, 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 plus. So here we have 2 changes of sign. Here we have none. So that's the negative first minus the positive. That should give the number. So there are 2 real signs. If you also take naught, then it's minus, minus, plus, plus. There's 1 change of sign. So this shows that we have 1 negative root and 1 positive root. So I gave you a wonderful technique, really. So it's worth knowing that it exists, and that proves that the equation that we arrive at has the equation here we arrived at has exactly 1 positive root, whatever it may be, 4 point something. So now I feel that I have answered problem 8 adequately. And I've also had the wonderful opportunity to relearn a technique that I've never mastered it. I knew it existed, but I've had forgotten it meanwhile.